Hi, my name is Sanjay Pujare, and I am an engineer in Google Cloud. I am in the gRPC team, and I'm a lead in the Proxyless service mesh
Hello,
team
everyone, and welcome to
within gRPC. Uh, in this talk, I'm going to cover a brief introduction to gRPC, an introduction to and a summary of the gRPC Proxyless service mesh, the Proxyless ecosystem consisting of XDS and Istio. Then we'll look at Proxyless service mesh features like traffic management and security. I'll then do a technical drill down using a deployment diagram. I'll also describe the gRPC programming API for using Proxyless gRPC. Towards the end, I'll cover the roadmap and what's coming. I'll also have a slide about various information resources for Proxyless gRPC. We'll then end with the Q&A session. gRPC is a popular glue protocol for stitching together your services in a mesh. It is the L7 networking layer that offers language-independent RPC mechanism for connecting services. gRPC uses HTTP2 and Protobuf. Although you can use other serialization frameworks, Protobuf is the most common. Note that Protobuf is a cross-platform, cross-language framework used to serialize structured data. Google developed Protobuf for internal use and then open sourced it. Uh, let's look at gRPC in the service mesh. A service mesh with proxies was the original model. This is how the service mesh started. Uh, in this, we have transparent proxies shown here in red boxes. They allow existing apps to be in the service mesh. Then the apps shown here in blue boxes, they are not aware of the service mesh. The proxies implement the service mesh transparently. Service mesh includes features like service discovery, routing, load balancing, security, and observability. Envoy is the most popular proxy and it is used in Istio. It supports HTTP, HTTP2, gRPC, and also L4 protocols. On the client side, Envoy intercepts requests or RPCs, applies service mesh policies, and sends them out. On the server side, Envoy receives requests or RPCs, applies policies, and forwards them to the local service. This diagram shows the flow of gRPC using Envoy in the service mesh. How about moving the proxy functionality into gRPC? So instead of a separate proxy sitting between the client and the server, in fact, two proxies, one on the client side and another one on the server side, can we just have gRPC absorb that functionality? Since gRPC is a popular framework for service-to-service communication, can we add service mesh features and awareness into it? With this Proxyless approach, the application layer itself would be unaware of the service mesh they are part of, but the service mesh policies would be transparently applied to the gRPC traffic by the gRPC library before the traffic is sent out from the client side. And similarly, the incoming gRPC traffic will be pre-processed by the gRPC library before delivering to the application. We now have a Proxyless service mesh where services talk directly to each other without any proxies. At this stage, let's talk a bit about something called XDS. XDS is a protocol for the control plane to talk to data plane elements. Hence, it's called a data plane API. Uh, XDS, where X stands for anything like X in algebra stands for any unknown quantity, and DS stands for a discovery service. For example, CDS for discovery of clusters, RDS for discovery of routes, uh, and LDS for discovery of listeners, etc. XDS was developed for Envoy, but it is quite open and extensible for any kind of a service mesh. gRPC adopted it and extended it for the implementation of the Proxyless service mesh. With this approach, a gRPC client receives the XDS configuration from the control plane consisting of route, cluster, and endpoint information, and it uses that to manage the outgoing gRPC traffic from the client side. On the server side, it typically consumes security and authorization information to enforce these security policies. By the way, you can also have things like fault injection on the server side to simulate faults on the server side, and XDS is used to configure such behavior on the server side. So how does one use this stuff, say in Java? The example here is from the gRFC mentioned in this slide, 829. Note that gRFCs are gRPC RFCs or proposals that are disseminated to the community and discussed and approved. So anyway, this particular gRFC describes the programming usage of Proxyless gRPC with security. I picked it up as an example because it was recently implemented by our team. And although I'm illustrating Java usage, the usage in C++, Python, and Go is quite similar. So let's look at the client-side usage first. There is an XDS channel credential that you supply to your channel builder, and this credential tells gRPC to use XDS supplied security configuration. On the server side, there is a similar server credential that instructs gRPC to use XDS supplied security configuration to the server. The XDS channel and server credentials allow the gRPC developer to opt in to the Proxyless or XDS, if you will, security configuration. What the developer is essentially saying is that I trust the XDS security configuration enough that I leave it to the XDS control plane to configure security for my application or applications. Note that the developer could use another credential here. For example, they could use a TLS credential or ALTS credential or even insecure credentials to force the usage of those security modes, even when XDS is used for, say, traffic management or load balancing. Wonder what the insecure channel credentials used inside the create method is doing? This is the fallback credential. Now, what is a fallback credential? This is the way the developer can tell gRPC library that in case the control plane does not supply any security information such as certs and keys to use, then use the security configuration uh, or information such as certs and keys. Use the security configuration as dictated by the fallback credential. This is the way a developer can make sure that their gRPC traffic has a certain minimum security mode, such as mTLS, even if the control plane is configured to not provide any security configuration to the data plane. This is a diagrammatic representation of how it all works. You have the client in the yellow box on the left sending RPCs to the server in the red box over a secure channel. The blue block on that line indicates a secure channel. Both client and server are XDS enabled and get their security configuration from the XDS control plane shown in blue at the top. The client and server need certs and keys that are provided by the certificate and deployment infrastructure to make it all happen. The green box represents the various infrastructure components of the certificate and deployment infrastructure, and these components are typically the certification authorities, also known as CAs, to mint certificates, a process to continuously generate CSRs and use them to mint the certificates, and then a mechanism to make these certificates and keys available to the gRPC workload using gRPC's plugin feature. For implementing security, we implemented a certificate plugin feature, and we also added the required extension points for that in XDS. When all of these things are put together, the client and server secure their gRPC traffic. Let's look at the flow in some detail by way of a sequence diagram for those of you who are familiar with XDS. I have three columns here, one each for client, the control plane, and the server. The client is the yellow box on the left, server is the red box on the right, and the control plane, that is Istio, is the blue box at the center. This shows the configuration steps from the control plane's point of view. The client is trying to access a service called payment.service, and it uses XTS colon / payment.service as the target string. So gRPC sends an LDS request, that is a listener discovery service request, to query an API listener for the payment service. The XTS control plane resolves it and sends the listener object for that payment service. The client then follows up with requests for further routing and cluster information for the payment.service. The client receives CDS and EDS payloads to help it set up connections to backend instances of the payment service. In this example, I have shown one instance here with the IP address 10.3.19.7 and the cert ID of mesh1/cluster2/SRV3. Note the SPIFFE colon prefix used in the certificate sans. We use the SPIFFE semantics and also something called server authorization. We don't have enough time to discuss the SPIFFE semantics and the server authorization in detail. I'll just say that server authorization replaces the hostname check in traditional WebTLS connections. So using server authorization, a client can verify that the backend it is talking to is indeed an authorized backend for the payment.service service that it was trying to reach. Server authorization is described in some detail in the gRFC 8.829 that I mentioned earlier. Now, on the right-hand side, the server in the red box receives LDS or listener configuration to help it set up its listener socket for the service. In this instance, the backend with IP 10.3.19.7 receives configuration to set up a TLS listener and bind it to port 8000. But there is more than just configuring the server socket or the listener, as we'll see now. Because of how XDS is defined in this context and how we have implemented it in gRPC, or Proxyless gRPC, you can have per connection security configuration. When the server receives a client connection, the server applies a filter chain from XDS, and the filter chain contains the required TLS configuration for that connection. A filter chain is a way to specify things like source IP or source port to characterize a connection. The filter chain also has the configuration to use a particular certificate with certificate ID of mesh1/cluster2/SRV3 for a given client connection. Once a filter chain applies, That is, the predicates in the filter chain match the connection attributes of the current connection. The security configuration from the filter chain is applied to the connection. So both the client and server receive the required configuration to set up mTLS connection between them. Configurations such as certificates and keys, whether TLS or mTLS mode, and what server authorization info to use, etc., etc. Having looked at security, let's look at some of the advantages of using Proxyless gRPC. In this slide, you can see the latency gains as the result of using Proxyless gRPC. Now some background on this experiment setup. This was set up using Fortio, which is a Go-based load testing app. The infrastructure resources used are as follows. This one used a GKE cluster version 1.20 with 3 nodes, each node of E2 standard 16 type. These nodes have 16 CPUs and 64 gigabyte memory each. The experiment uses the Fortio client and server apps in the application container, and uh, each container is allocated 1.5 virtual CPU with 1000 megabyte memory allocated to it. Then we also have the sidecar container for the Istio agent and Envoy proxy, which has one vCPU and 512 megabyte memory allocated to it. The experiment included testing with and without mTLS enabled and with and without the Envoy proxy. Uh, Now, a little bit about the sidecar container. If this is a Proxyless test or experiment, why is there a sidecar container? Note that we did the experiment to measure the performance for both the cases, proxy based and Proxyless. In case of Proxyless, there is no Envoy proxy, but we have the sidecar container for something called an Istio agent. So even though we don't need the Envoy proxy, we need the Istio agent. I'll talk about this in some detail in a later slide when we discuss the agentless mode. Uh, Now let's compare the performance. Compared to the Envoy case, there is a massive improvement. With mTLS at 64 connections, the latency improvement is about 6 times. And overall, there is about 6 to 16 times improvement. That is almost 500% to 1500% improvement, depending on whether you see P50 or P99 latency numbers. Now, this is still with advanced traffic management features and mTLS are present, but without the Envoy proxy. Uh, let's look at the resource usage. As mentioned earlier, the Proxyless experiment still requires an agent called the Istio agent. Even though we still require an agent, the agent uses less than 0.1% of a full virtual CPU and only 25 megabytes of memory, which is less than half of what running Envoy requires. Note that these metrics don't include the additional resource usage by gRPC in the application container, but all the same, the slide serves to demonstrate the resource usage impact of the Istio agent when running in this mode without the Envoy proxy. Uh, let's look at the current status and what's coming as per our roadmap. We currently have experimental support for Proxyless gRPC with Istio in Go and C++. We'll be extending Proxyless gRPC support for Istio in all languages. The current Go and C++ support will be extended to Java and then to C Sharp, Python, and other languages that gRPC supports. We'll also be extending the various Istio observability features to make Proxyless gRPC observability on par with proxy-based Istio. This would entail adding support for metadata exchange or peer metadata for fine-grained telemetry and allowing the user to visualize their service mesh. The user would also be able to see gRPC specific metrics and other observability data such as latencies, volume, debug logs, and call tracing information. Uh, I briefly talked about the Istio agent in a previous slide. Currently, Proxyless gRPC in Istio still requires the Istio agent. The agent does bootstrap generation, certificates, and key generation, and it also acts as the XDS proxy. Because of its XDS proxy role, gRPC does not need to communicate with the Istio control plane directly, nor does it need to provide any control plane credentials. Note that the Istio agent is the same agent used with Envoy. gRPC communicates with the Istio agent over a Unix domain socket, which is considered a local and secure connection. Ideally, we would like to make the solution proxyless as well as agentless. This will require getting rid of the Istio agent. Once we add the additional authentication features to gRPC and enhance Istio to provide bootstrap and certificate functionality through an alternative mechanism, we will get rid of the Istio agent. And then we will have a truly proxyless and agentless Istio implementation of gRPC. We anticipate that the mode with the agent will continue to be supported for the foreseeable future for various advantages it offers, such as a common agent for Envoy and gRPC that has the latest control plane authentication implementation for various Istio environments we want to support. In this slide, I have included some resources to get more information about Proxyless gRPC. The first five are gRFCs, which contain technical description of various things we discussed earlier, specifically starting with XDS load balancing, then XDS in servers, uh, another gRFC describing the Proxyless gRPC security, on which I had two slides. Then Java channel and server credentials, which we also saw in one of the slides where I described how to use this stuff with Java. And finally, a gRFC about RBAC or authorization with Proxyless gRPC. I also have a couple of links. First one is an Istio blog about Proxyless gRPC. And the last one is a Google Cloud blog that talks about Proxyless gRPC with a Google Service Mesh product called the Traffic Director. So that concludes the presentation, and I would like to thank you. And I open it up to for any questions you might have.